Welcome to lecture series on CFD part 1. This is lecture 7 on Introduction to Finite Volume Methods. In this lecture, I'll first describe the principles of finite volume methods and then present the basic approximations for surface and volume integrals. The next step are basic interpolation methods, which are needed to compute convection fluxes, and approximations of gradients at control volume phases, which are needed to compute diffusion fluxes. I will show how the order of integral approximation and interpolation can be analytically determined using Taylor series expansion, but at the end I'll also present numerical experiments by which this can be demonstrated. Such experiments are especially important to determine the overall order of flux approximations because they always involve two levels of approximation. Finite volume method is the most widely used approach in CFD. All major commercial codes and OpenFOAM are based on finite volume approach. The starting point in finite volume methods are conservation equations in integral form. In this and the next two lectures, we shall deal with a steady-state conservation equation for a generic scalar phi. On the left-hand side, we have convection fluxes through the control volume surface, and on the right-hand side are diffusion fluxes through the control volume surface and the volumetric source terms. This equation is valid for any control volume, no matter how small or large. In fact, it is also valid for the solution domain if it is considered as a one large control volume. Finite volume methods can be applied to control volumes of any shape, that is, polyhedra with any number of faces. The above equation is applied to each control volume and fluxes and source terms are approximated. The result is one algebraic equation per control volume in which variable values at cell centroids are unknowns. For the whole solution domain, a system of algebraic equations needs to be solved. We consider first two-dimensional Cartesian control volumes as shown in this figure. Compass notation is used to denote control volume faces and neighbors: east, west, north, and south. A face describes the part of the control volume surface which is either common to two control volumes, in which case it is an internal face, or it coincides with the solution domain boundary, in which case it is a boundary face. Shown are also unit vectors normal to cell faces. Computational points are in cell centroids. There are also other possible arrangements, but for the sake of simplicity and generality, we stick to cell centroids. The integral equation is applied to each control volume. How are the individual terms approximated is shown in the following slides. The integral over the closed control volume surface is equal to the sum of integrals over its faces. For the sake of simplicity, we shall first consider an arbitrary function f and see how it can be numerically integrated over the face sk. In our transport equation, f stands for the flux vector component normal to cell face. In the convection term, f is the product of density transported variable phi and the velocity component normal to the face. In the diffusion term, f stands for the product of the diffusion coefficient gamma and the gradient vector component normal to cell face, which is the derivative of phi with respect to n, the local coordinate directed normal to the cell face and pointing outward. Finite volume methods require for both convection and diffusion fluxes two levels of approximation: approximation of surface integral over the cell face and interpolation of the function phi to the integration points in the case of convection flux, or approximation of the derivative of phi at integration points in the direction normal to cell face in the case of diffusion flux. The simplest approximation of an integral is the midpoint rule. The integral is approximated by the product of the integration function f at the centroid of the face, fe, and the area of this face, se. The function value at the face centroid is assumed to represent the mean value of the function of the face, which is where the approximation comes from. The approximation is exact for a linear variation of f over the cell face. Midpoint rule is an approximation of second order. This will be demonstrated in the next two slides. Variable values at the phase center must be expressed through cell center value by interpolation. To retain the second order of integral approximation, interpolation should also be of second order or higher. Another second order integral approximation in 2 dimensions is the trapezoid rule. Here we need the values of the function f at the 2 integration points, cell corners. Therefore, the variable values need to be interpolated to cell vertices. Let us now find an expression for the leading term in the truncation error of midpoint rule approximation to verify that it is a second order approximation. We consider the east face of a control volume and set the local Cartesian coordinate system with its origin at the phase center E. The y coordinates of the 2 corners are then minus delta y half for SE corner and plus delta y half for northeast corner. Now we write the Taylor series expansion along y coordinate for f around the location E. H contains all higher order terms. We can now integrate the function f analytically from SE to NE. Note that the derivatives of f with respect to y at location E are unknown, but at the fixed location they are not function of the coordinate y and can be treated as constant in the integration process. This makes the integration straightforward. The final expression now needs to be evaluated for the integration limits. Terms with even powers of y drop out because E is midway between NE and SE. The limits are of the same magnitude but opposite sign. Fe times delta y is the midpoint rule approximation, and the next term is the leading truncation error term. All high order terms are contained in H. The local truncation error term is proportional to delta y cubed, but when we do grid refinement, we have a finite integration domain with n segments, and n doubles when grid spacing is halved. Because the error is incurred n times and n equals s over delta y, the global error is proportional to delta y squared. This confirms that the midpoint rule is a second order approximation. The second order of midpoint rule will also be confirmed by numerical experiments in slides 19 and 20 for the complete convection and diffusion flux terms, accounting for both levels of approximation explained in slide 6. In finite volume methods, conservation equations also contain volume integrals which need to be approximated, in the rate of change term and in the source term. See slide 7 for mass conservation, slide 11 for momentum conservation, and slide 15 for the conservation of generic scalars in lecture 3. The simplest second order approximation of volume integral is again the midpoint rule. The cell center value of function to be integrated over the cell volume, here denoted by Qp, is assumed to represent the mean value of Q over the volume, which is where the approximation comes from. The approximation is exact for a linear variation of Q over the cell volume. Because all variables are computed and stored at the cell center, no interpolation is needed. The approximation is also valid for any polyhedral shape of the control volume. All major commercial CFD codes and OpenFOAM use midpoint rule to approximate surface and volume integrals. We now turn attention to the second level of approximation, interpolation. To compute convection flux using midpoint rule, we need variable value phi e at the phase center. The simplest approximation is to assume that this value is equal to the value at the cell center on the upstream side of the phase, that is phi p if fluid flows out of cell across phase E or phi e otherwise. This is called simply upwind or backward approximation. To complete the computation of convection flux, we also need the product of density and velocity component normal to cell phase. We assume for the time being that this quantity is known. In any case, density and velocity also need to be interpolated from cell center values to the phase center. Taylor series expansion in x direction centered at P leads to the following expression for phi e, assuming u greater than 0. Phi p is the upwind approximation, and all other terms from the series represent the truncation error. The leading term is proportional to delta x, so it is a first-order approximation. The leading truncation error term from convection flux resembles the diffusion term. Compare the expression on the left, which is the true diffusion term, and the expression on the right, which is the leading truncation error term from convection flux. This is why discretization error associated with such first-order schemes is called numerical diffusion. The numerical diffusion coefficient is obviously equal to rho times u times delta x half. We see that on coarse grids, this coefficient can be large compared to the physical diffusion coefficient and thus lead to large errors. The effects of numerical diffusion on solution will be demonstrated in exercises to be presented in Lecture 9. The next obvious interpolation method is the linear interpolation, which will set center values on either side of the face as shown in this figure. This means assuming that the variable phi varies linearly from P to E, as indicated by the red line. Because linear interpolation in the integral equation used in a finite volume method is equivalent to a central difference applied to the first derivative in the differential equation used in finite difference method, this interpolation approximation is often called central differencing scheme, although no differentiation is here involved. This is the expression for linear interpolation to location E, with interpolation factor lambda E defined by this expression. Let us determine the order of this approximation. Taylor's series expansion around node P leads to the following expression for phi at face center and at the center of the neighbor cell E. By using the second expression to eliminate the first derivative in the first expression, we obtain the following expression for phi E. The first two terms on the right hand side represent the linear interpolation, and the rest is the truncation error. We see that the leading term is proportional to delta x squared, irrespective of whether the grid is uniform or not. Linear interpolation represents therefore an approximation of second order. There are more options when we assume a linear variation of the variable in the vicinity of the face E. A linear profile can be defined by one value and the slope, the equation of a straight line. If we pick the variable value and the gradient at the upstream cell center, we obtain the second order upwind scheme. For example, for u greater than 0, it is this expression. We used this expression already in the previous slide. It follows directly from Taylor's series expansion around node P and shows us the leading truncation error term. It is proportional to grid spacing squared, and hence the blue framed part is a second order approximation. This scheme requires deferred correction to be implemented in an implicit solution method. Usually, first order upwind is used as the lower order scheme. The difference between higher and lower order approximation is then the term involving the first derivative at the upstream cell center, which can be computed explicitly using variable values from the previous outer iteration and added to the source term. Note that to retain the second order of this scheme, the first derivative must also be approximated with at least second order. Another option is to use linear extrapolation from two upstream cell centers, as indicated by the red line in the figure. By using Taylor's series expansion around P to express the variable value at the west neighbor cell center W, to eliminate the first derivative in the above expression, we obtain the following expression for phi E. The blue framed part is the linear extrapolation from W and P to face center E, which is used as an approximation for phi E, which is often called linear upwind scheme. The red part represents the leading truncation error term. It is also proportional to grid spacing squared, so this is also a second order approximation. Thus, all three schemes based on the assumption of linear variation of the variable phi in the vicinity of the face are second order approximations. On a uniform Cartesian grid for u greater than 0, linear upwind scheme leads to the following expression for extrapolated variable values at E and W phase centers. The scheme thus refers to more distant nodes like WW and N, EE, and so on. If implemented directly, it leads to a larger computational molecule requiring more memory, a different linear equation solver, and more computing time per iteration. The scheme is therefore usually implemented using deferred correction approach to keep the computational molecule limited to nearest neighbors around P. The second order upwind scheme described at the beginning of the previous slide is the default scheme for convection in SimCenter StarCCM Plus code. To compute diffusion flux through a cell phase, we need an approximation of the derivative of phi in the direction normal to the phase. At phase E, we need the derivative in x direction. The most straightforward approximation of the derivative at a cell phase is the central difference. The value at the right neighbor minus the value at the left neighbor divided by distance between them. This approximation, or an equivalent of it, is used in all major commercial CFD codes and in open form. By using Taylor series expansion around phase center E to express variable values at P and E, one can easily derive the following expression for the two leading truncation error terms. The leading term is proportional to delta x, but it vanishes when the grid is uniform. However, if the grid is systematically refined, the leading truncation error term reduces with second order, as shown in slides 13 and 14 of lecture 4. The above approximation is based on the assumption of a linear variation of phi between the two cell centers, P and E. An approximation which accounts for grid non-uniformity can be derived by fitting a parabola through variable values at 3 points, for example, 2 on the upstream side and 1 on the downstream side. Another possibility is to use a compact approximation. Fit a parabola to variable values at cell centers P and E and phase center E. The resulting expression is the one given in slide 12 of lecture 4 with I equal E, I plus 1 equal capital E, and I minus 1 equal capital P. The variable value at phase center E needs to be obtained by at least second order interpolation. It can be conveniently implemented using the deferred correction approach. Let us now perform some numerical experiments to test the order of various approximations. For some schemes we have derived expressions for the leading truncation error term, but this is not so straightforward to do for the complete flux approximation because it involves both the approximate integration and interpolation or differentiation. Numerical experiments are equally simple for linear and nonlinear terms. We test the order of various approximations by computing approximations of surface integral over a given area using systematically refined grids and variable values at cell centers taken from an analytical function. Here, the following polynomial function is used. Discretization errors are determined by comparing approximations with the exact value of surface integral obtained by the analytical integration of the function. Interpolation and approximation of cell phase gradient are included in integral approximations. This figure shows the two-dimensional grid and two levels of refinement. Integration area is the east face of one cell at the coarsest grid level, shown here by the red thick line. Each time the grid is refined, the number of faces over which the integration needs to be performed doubles. All these integrals are summed up so that the integral over the same area on all grids can be compared. First, we check the order of interpolation alone. The left figure shows how the value at the center of the phase changes as the distance of neighbor cell centers changes through grid refinement. This is checked by refining the grid in x direction alone, because when the grid is refined in both directions, the location of the cell phase center moves to another location, but we need it to stay fixed to check the convergence with grid refinement. Shown is the exact variable value at the location E from the analytical function and the interpolated value from the backward approximation or upwind labeled BD, green line. linear interpolation labeled CD2, the blue line, quadratic interpolation labeled quick, red line, and interpolation by a cubic polynomial labeled CD4, the gold line. Quick, third order, and CD4, fourth order will be described in lecture 8. We see that all approximations converge monotonically toward the exact value, but BD is, even with the finest resolution, still significantly in error. Also, not all approximations approach the exact value from the same side. Quick underestimates, another scheme overestimates the exact value on coarse grids. The right figure shows how the error changes as the grid spacing is reduced. All interpolation methods converge with expected order. For the first order upwind scheme, BD, the error reduces one order of magnitude when grid spacing is reduced one order of magnitude. For linear interpolation, CD2, the error reduces 2 orders of magnitude when the grid spacing is reduced by the same order. With quadratic interpolation, quick, 3 orders of magnitude reduction is achieved, and for cubic interpolation, CD4, the error reduces 4 orders of magnitude when grid is reduced by 1 order of magnitude. The cubic interpolation is by far the most accurate one. This slide shows the variation of the computed convection flux through the total integration area on the left and the error in the numerically computed integral on the right. Midpoint rule is used to approximate the integral, and 5 different ways of computing the variable value at the midpoint are used. Exact value at the phase center from the analytical function, labeled analytic, which gives the order of the integral approximation alone. The backward or upwind approximation, labeled BD, the green line. Linear interpolation, using cell center values on either side, labeled CD2, the blue line. Quadratic interpolation, using cell center values at 2 upstream and 1 downstream cell, labeled quick, the red line. And cubic interpolation, using cell center values at 2 upstream and 2 downstream cells, labeled CD4, the golden line. We see that all approximations converge monotonically toward the exact value. Upwind approximation overestimates, and all other approximations underestimate the exact value on the coarser grids. As expected, the error reduces 1 order of magnitude when the grid spacing reduces by the same factor if the first order interpolation BD is used. Both linear interpolation CD2 and midpoint rule for integration are second order approximations, and the 2-level approximation also converges with second order, as the blue line shows. Interpolation with an order higher than second does not lead to a higher accuracy of the flux approximation. Even when the exact analytical function value at the phase center is used, the overall approximation converges with second order, which is the order of the integral approximation. The errors obtained with cubic interpolation and with the exact value at the phase center almost coincide, except on the coarsest grid. Most interestingly, the error is significantly smaller when linear interpolation is used than with any other higher order interpolation. This is because the errors from 2 approximations, interpolation and integration, in the case of linear interpolation, partially cancel out. As shown in the preceding slide, CD2 overpredicts the phase value, and here we see that midpoint rule underpredicts the integral. The 2 effects thus compensate each other. This slide shows the variation of the computed diffusion flux through the total integration area on the left and the error in the numerically computed integral on the right. Midpoint rule is used to approximate the integral, and 4 different ways of computing the gradient at the midpoint are used. Exact value at the phase center from the analytical function, labeled here analytic, the green line. Central difference using cell center values on either side, labeled CD2, the blue line. Compact Padé approximation of 4th order, labeled Padé 4, the red line. And 4th order central difference using cell center values at two upstream and two downstream cells, labeled CD4, the golden line. We see that all approximations converge monotonically toward the exact value. All underestimate the exact value on coarse grids. Both central difference CD2 and midpoint rule for integration are second-order approximations, and the two-level flux approximation also converges with second order, as the blue line shows. The error reduces 2 orders of magnitude when the grid spacing is reduced by the same factor. Approximations of the derivative at the cell phase center with an order higher than second does not lead to a higher order of the flux approximation. Even when the exact analytical value of the derivative at the phase center is used, the overall approximation converges with second order, which is the order of the integral approximation. The errors obtained with the compact fourth order approximation and with the exact value at the phase center almost coincide except at the coarse grid. However, the error is almost 1 order of magnitude smaller when fourth order gradient approximations are used, but the convergence of flux approximation is second order in both cases. Let me now briefly summarize the main takeaways from this lecture. Finite volume methods require 3 kinds of approximations: approximation of surface and volume integrals, interpolation from cell centers to integration points at cell faces for convection fluxes, and approximation of gradients in integration points at cell faces for diffusion fluxes. Midpoint rule is the most widely used approximation for integrals. It is a second-order approximation and is applicable to any volume or surface shape. Linear interpolation, also known as central differencing scheme, and linear extrapolation, also known as linear upwind scheme, are the most widely used second-order interpolation methods in CFD. First-order upwind approximation for convection is too inaccurate and should be avoided. Gradients at cell faces are usually approximated using second-order central differences. The solution converges with the lowest order of the 3 approximations listed above. It is therefore advisable to use methods of the same order for all approximations.